So hello everyone, my name is Victor Araman, and I'm a professor of decision science here at the Alain School of Business. I want to start by welcoming you all today for this unique event in many ways, organized by the Center of Advanced Mathematical Science, CAMS, and the Alain School of Business. I'm going to leave the floor for a couple of minutes to Jihad to introduce the center and say a couple of words. I will also say a couple of things before I leave the floor to René. Please, Jihad.
Thank you, Victor. Thank you all for joining us today for the kickoff of a very exciting thematic program for us at the Center for Advanced Mathematical Sciences at the American University of Beirut. I've taken over as a director more than 2 years ago, and specifically with the mission of making sure that the center contributes to mathematical sciences, both applied and pure, in relationship to the various manifestations of the field at AUB and in the region. And so we've had thematic programs in mathematical physics. We hope to have them in pure math, whether in number theory or complex geometry, which are fields that are represented in our university and of relevance to neighboring universities. And today I'm particularly excited to be kicking off this collaboration with the business school around a theme which is of particular interest to us, both in view of the mathematics involved, the breadth of the mathematics involved, the beauty of the results, as well as their multifaceted applications. And it is in discussion with my colleague Victor Araman that I got to learn about the tools, the background, the history of the fields, as well as their applications. And I couldn't be more excited about this collaboration, which brings Victor directly, intimately involved with the activities of the center, brings us in collaboration with the Alain School of Business, having had previous collaborations around data analytics with the school, around an extended program which has brought together, thanks to the efforts of Victor and his network of distinguished scholars, brought together a fantastic array of people covering a wide range of topics, which I understand will be handled systematically over a period of a few months through mini courses and seminars, and eventually discussions that will touch on fundamental applications that are increasingly urgent in our world of networked activities and their disruptions. I'm personally very much looking forward to proceedings. I may not be able to follow it all, but I will certainly be reviewing the recordings. And I look forward to that significant and numerous participation for the remaining of the event. And I have Victor and his colleagues to thank for their enthusiasm and what I hope will set a precedent for the field in the years to come. So once again, Victor, thank you very much. And René, great to be kicking off the event with you.
Thank you, Jihad. I just need to say a couple of words as well. I promise I will not do that every time. That's just because of the starting of this, quite unique, as I said, program. So before I introduce René, let me just say a couple of words. First, I just checked those registered. Indeed, we're at 155 participants right now, but more than 315 actually registered, and the audience is quite broad. 30% comes from North America, 25% in Europe, 10% from South America, 8 to 10, and Middle East and North Africa around also 25%, and East Asia is also very well represented, whether China, India, Hong Kong, Singapore. So really an amazing audience and very broad. What is also quite exciting that we're going to be talking about modeling, mathematics, and pricing. And in many ways, I actually consider myself a citizen of the world. In this particular case, I'm very proud and thrilled that this is happening out of Lebanon and AUB in particular. In particular through the times that we're going through here, it's really great to see all this actually meeting and centered around or the kind of initiated by AUB and in Lebanon. Let me just say thank you first to Jihad's vision, because when I approached him, really he was extremely supportive, and not only that, I mean, the way he saw things were much bigger than what I initially had in mind and envisioned in many ways. I want to thank the steering committee of CAMS, who was also very supportive, in particular Ayman Kashmar at the Lebanese University, Hiba Hamoud, the executive administrator, really amazing job behind the scene and will continue doing so as expected to some extent, but really fantastic job. I want to turn also a couple of words about the contributors in general. Basically, when I connected first with René and Omar, who will be actually talking at the end of next week, and just throw on them the idea, and both of them were extremely enthusiastic. And so as a result of that, I basically got even more encouraged, contacted few people, and I want to thank all 8 of them: René, Omar, Gustavo, Hussein, Arnoux, Philippe, Florent, and Gabriel, who will be actually covering different topics basically until end of February. But what I want to insist is this, and I think it's an important point, particular message for those PhDs and joining the academic world, hopefully. I just took me an email explaining the idea, and everybody basically just got excited without really checking the details. They were more, on board. We had one meeting on Zoom. We agreed on the scope, thought about it, gave me their, feedback, thought up, about who is the reach, who are the target, and so on. And eventually it was a really smooth schedule. And, all these guys are extremely, not only accomplished researchers, but extremely busy. And, just this very humble and very a quick reaction and acceptance of this really says a lot about them as people, but to some extent also about our community. That's basically, it's about research and working very hard, but also it's about, sharing that knowledge in many ways, and that's what we're hoping to do here. Quick reminder of the plan. Basically, we're going to start with dynamic pricing, and it's all on the website, of course, and you probably all visited it. But just quickly, in November, this first theme is going to be on dynamic pricing and revenue management. By November 18, will be done. November 30th, start the second theme on choice modeling. Again, another 4 sessions, 3 sessions and a seminar. The third theme on dynamic learning will start after the Christmas break, basically on January 17, and will end on January 28th. The last theme, which is about platforms and revenue management in that context and modeling platform per se, is going to start on February 10th and will finish with a seminar on February 25th. Having said all this, quickly introducing René. I mean, first, René was initially a colleague at NYU where it all started. And we always had in mind to actually do a conference together and with Gustavo, and maybe this is a second trial in that regard. So René also is a co-author and eventually a great friend. He's basically his research is on stochastic modeling in general, with application to revenue and retail management, queuing theory, and finance. He published in journals ranging from applied probability journals, econometrica, so economics, but also management science, math of OR, MSOM, OR, POM, and so on. He also held in most of these journals editorial position as well. He joined after NYU. He joined the booth as a professor in the Department of Operations. And before joining NYU in 2001, he worked for the Chilean Central Bank and taught at the University of Chile and at Sloan MIT. He received his Master's of Arts in Civil Industrial Engineering from the University of Chile and his PhD in OM from MIT. I just say one thing about René. Even though he's very driven by practical problem, I have to say he gives so much importance to mathematical rigor and elegance. So I cannot see a better way to actually kick off this program than with him. So thank you, René, for accepting, and I leave you all with in great hands. So enjoy the program. Thank you.
Thank you, Victor, very much for that nice introduction, Jihad. Thank you so much for the invitation. It's really nice for me. I like Victor. I think this is a fantastic idea that we can, have this type of events where we can try to share some of the work that we have been doing in some communities and try to expand that in other communities and try to see the opportunities to join collaboration. So I think this is a fantastic program. As Victor said, the whole month and a half, 2 months, I think has been thought in a way that there's going to be continuity, and hopefully as you move through the different topics, you will see how the applications and the mathematics are getting blended together and are creating opportunities for important research. And by that I mean research that is on one end theoretically elegant, theoretically challenging, and also, and probably more important in some sense, in my view, it has practical applications. It's really impacting the world out there. It's helping companies actually make better decisions. It's helping consumers and society make better decisions. And in many ways, that's what we're trying to do here, right? So the way I would like to start is by kind of giving you some sort of a introduction to the field of revenue management and pricing, kind of try to build the foundations of what this field is all about. And then as the next modules continue, you will see how this field has been evolving and expanding, incorporating new aspects. And so hopefully by the end of this program, you're going to have a very strong background of this field, and hopefully will help you ideally start doing work on this area. Okay, so all right, so let me start. And the way I would like to start is by trying to give you roughly, and I know that you're here more for maybe for the mathematics of this, and that's fine, but I think it's important for all of us to have a good sense of what are the applications and what do we have in mind when we think about revenue management, what we're trying to achieve. And again, many of these things will come up later in different courses. And so as we move forward with the program, you will start seeing the applications coming more clearly. But I think it's important to start with some background. And so there's this very famous quote that folks from American Airlines came up with. Here we're talking about, early 1980s, right? So about 40 years ago is one can think of the origins of many of the ideas that we are going to be seeing in this program. So revenue management started in the airline industry. And so folks from the American Airlines that were working on some of these issues came up with this quote, which is kind of trying to summarize what we're trying to do here, which is selling the right products to the right customers at the right price and the right time through the right channel. So somehow, if I try to summarize this, the way we're trying to do here, we're trying to be smart and efficient in the way we do allocations of resources to consumers, right? And so if we take the airline, which is kind of the example that I'm going to be using for the most part today, you can think about an airline managing seats on different planes, throughout their network, right? And a company like American Airlines, just to give you a sense, might be managing more than 4,000 flights daily, right? And every flight will have, anywhere between 100 and 500 seats. And so there's a lot of capacity that needs to be managed. There's a lot of capacity that needs to be allocated into the market. And so when American Airlines is trying to think about doing revenue management, is trying to think about how should I manage that seat, right? It's not thinking about how should I manage my overall capacity on the network, right? But rather, how should I manage the capacity of that individual seat on that flight that might be departing, say, from Beirut to, I don't know, Paris, right? So it's a very hands-on process. It's a process of trying to understand, A, what's the value of that resource from the customer perspective, B, who are the potential consumers that seat might have, and then how we do this allocation dynamically over time. And so one of the central points, I would say, in revenue management is trying to understand that value. What's the value of that unit of resource? And what is very important is going to come up, I suppose, very clear today, is that that notion of a value is not a static quantity, but rather is a dynamic quantity. It's a quantity that keeps changing over time. It's a quantity that changes stochastically over time. So when we think about, understanding the value of a resource, is really trying to characterize some sort of a stochastic process that might describe the value of that resource over time. And if a company and a manager is able to understand that process, that stochastic process that describes the value of resources, then that manager and that company is going to be in a particularly good position to start thinking about how to allocate that and how to, if you want, sell that resource in the marketplace, right? And so, of course, airlines is the prototypical example, right? And I think it's important to know that major and not so major, really, airlines these days have a very strong revenue management department. For most of them is at the core of their business, and they would not be able to become profitable and survive over time if they don't have people doing the type of things that we're going to be learning today and in the following sections. Now, of course, when you start thinking about that, you will have hotels, which is another industry that have been developing revenue management for many, many years. And the kind of problems that they face is very similar. You have rooms in different units, hotels throughout their networks of hotels that they manage. And the question that they're trying to think about is how should we value this type of resources and how should they price them and put them in the marketplace, right? Now, one thing that becomes very important when we start looking at these two examples is that these resources are perishable, right? So if you don't book a room on a particular night and that room is empty, that is a unit of resource that perishes. You cannot use it later on, right? And so sometimes people have called revenue management perishable asset revenue management. And the idea is to emphasize the fact that for many of these applications, the perishability of the resource is extremely important. There's some sort of a deadline that somehow pushes you and forces you to find ways in which you want to sell this resource on the marketplace, because if you don't meet those deadlines, those resources would just go without being used, right? Now, retailers managing shelf space is an example. Cargo companies managing containers and capacity on the logistic network is another example. You can think about, parking companies, right? As a few months ago, I was talking to a company here in the Chicago area that is trying to push more and more revenue management in the way they manage their parking space throughout the city, right? And how they think about, selling these spots over time and dynamically. Victor has done a lot of very nice work on the space on online advertisement. And so if you think about an example like this, you have the New York Times, and the New York Times, of course, is providing content in the forms of news and information, but also is selling advertisement like this banner that you have here, right? And so that's a piece of space, a piece of capacity, if you want, that the New York Times is managing. And what they need to figure out is how to sell that to advertisers that might be willing to post their ads, right, in this type of media outlet, right? Again, you can think about this as a resource that the company is managing, and then the question is how you should do the management of that type of resource, right? So that's basically what we're trying to do here. And again, we can spend a lot of time going to more and more of the applications, and I think it's important for you to try to think about them, but I want to focus on the tools so that we can, over time, start seeing more how these interact with each other. But we are, in some sense, today trying to think about how we do optimal resource allocation. And so this is some sort of a snapshot of some of the type of resources that one can potentially think of. Now, the other thing that I want to mention is that revenue management is also a system. So at the end of the day, for these tools to really make sense, is they have to be implemented in practice, right? And so at the end of the day, the goal is to be able to develop models and algorithms that can be implemented, which means that we need to be practical. We need to have a sense of implementability, right? So if we try to abstract some of these problems mathematically and try to bring them to a level of abstraction that might be very nice for the mathematics that we might be developing and the analysis, but those are not going to be able to translate very clearly into applications, then I would say that you're not doing good revenue management, right? Because in some sense, for this ideas to really work, you need to be able to implement them in practice, right? So this is a very concrete, down to the earth. That doesn't mean that you can start with a very theoretical, abstract problem. You can try to understand the essence of that problem, and over time start, bringing that theory into practice. But you shouldn't forget about that. I think it's very important that we always keep that in mind, the back of our heads, that what we're trying to do is to try to develop tools and algorithms that will impact practice, right? And so this is some sort of a diagram that describes how the system will look for, say, again, an airline, where you have different layers in terms of data collection. So, a lot of data analytics is needed in order to do good revenue management, because you need to forecast demand. You need to understand those processes that describe valuations of your consumers. And that means that you need to understand the market and have enough data and analytics that can help you do that. You have the bottom part here is kind of the distribution of these ideas, right? So once you start deciding on how to sell your resources and how to price them and how you allocate them, you need to communicate those decisions and those policies to the marketplace. And in the case of the airline, this can go through your website, or this can go through travel agencies that will connect to your global distribution systems, right? So you have some sort of a bottom part here that is in charge of translating your models and tools and ideas and policies into concrete actions. And it's really in this middle level where we see the revenue management that we're going to be discussing in this class, which comes in the form of demand forecast estimations, right, and optimization, right? So this is a combination of analytical tools and algorithms, plus the use of human that will interact with those tools that will potentially make them applicable, right? And this is also important, that many of these tools will interact with human beings, and so we need to be able to kind of keep that in mind, so that we make them as user-friendly and intuitive as possible. All right. So okay, but the point is that for us, we're going to be living somehow in this space of this system, where we're going to think about the forecasting and the optimization. And for the most part, for me, I'm going to be focused on the optimization side of things. But then as you move forward, so next time that you meet in the next module, you're going to be talking about consumer choice models. And a lot of what comes when you start thinking about consumer choice models is really to understand, how to do this forecasting, how you model demand, and how to do the analysis that goes with it. All right. Okay, so let me try to bring this to a level of concreteness that would be useful for today's discussion. So think about the following example. So think about, again, an airline. The airline has a certain level of capacity, let's say 90 seats that the airline is trying to sell. And let's say the airline has been able to segment the market in 3 classes, right? And so the different ways in which you can do these segmentations, and you can screen your customer types. They might be through whatever channel they're using to purchase this. So some people might buy on your website, some people might buy through, travel agencies, and so on and so forth, right? And so the idea is that here we have these 3 demand segments, and each one somehow is willing to pay a different amount for essentially the same resource, right? The same seat, right? Now you might start asking yourself, well, how can they be willing to pay different prices for the same seat, when a seat and this product might look like a commodity, right? If you're flying from Beirut to Paris in a coach seat, you might say, well, why people are willing to pay different things? But that's where creativity and somehow understanding of the market can help, because maybe this seat is fully refundable, while this one is not, right? Maybe these seats need 2 or 3 weeks advance purchase, while these ones do not, right? So you can start modifying what a product is. The physical product is the same as a seat on an aircraft, but then around that physical product, you put other type of features that differentiate products and will allow companies to sell them at different price points, right? And so just to give an idea, an airline might be selling the same seat, the same coach seat, at more than 20 or 30 price points at any given moment in time, right? So there's a huge amount of dispersity, if you want, in terms of the market that you're serving. And many times these prices are attached to some of these constraints that I was mentioning, like refundability or advanced purchase, or other type of characteristics, right? Now, for us, the optimization problem is, well, should we accept or reject this request, right? So of course, if someone is willing to buy a seat for $800, which is the maximum price, you're gonna accept that. But what happens if you have a customer that is willing to buy this at $400, is coming up to you and say, I want a seat. Do you want to sell this or not, right? And you can imagine that the trade-off that you are experiencing here is that if you say yes to this person, right, you're gonna get 400, but you're gonna deplete your inventory by 1, which means that potentially, as the selling process evolves, you might eventually run out of seats, and you're not gonna be able to maybe sell seats to people that are willing to pay 100, right? So you're taking some sort of a risk. Every time that you allocate a resource, you are somehow incurring an opportunity cost potentially of selling that seats to a better customer, to a better price point in the future, right? And so yield management is about thinking about how to do this effectively and how to try to find ways in which we maximize the allocation process that goes with this activity, all right? So how can you do this, right? So if you look a little bit at the origins of how people were doing this in some sort of from a, let's say, historical perspective, the first approach was to use what's called partition booking limits, right? And so partition booking limits would say, let me take my overall capacity, which I'm reflecting here by this bar here, and let's say this capacity is C units of 90 seats in my previous slide. And then you would say, okay, I'm gonna partition those 90 seats and I'm gonna put Q1 of them to serve class 1, Q2 of them to serve class 2, and Q3 of them to serve class 3, right? And then what you will try to do, you will try to be smart in the way you think about this partition by looking at demand forecasts, trying to understand how much demand you expect to see from each one of these classes, trying to see what prices you're gonna collect or average prices you can collect from these segments, and then try to optimize over these quantities, right? So this is very easy to implement because in some sense, you're gonna be able to just allocate those seats to each. So it's like having 3 separate inventory levels for each demand class, and then you can manage those inventories independently. Now, of course, if you take a moment to think about this, it might be easy to implement, and that's why this was, very useful from a practical standpoint. But from a revenue management or yield management standpoint, it's extremely inefficient. Because let's say this class is the most profitable one. So this is the class that is willing to pay, say, $800. So what happened if, for whatever reason, your forecasts were not accurate, you ran out of seats, right? And now you don't have more of these seats that you want to sell to the most profitable class, while you still might have seats left for the less profitable class, right? So when you partition and you allocate resource independently, you are obviously losing opportunity of selling better seats as demand progresses, right? So easy to implement, very poorly in terms of yield management. How you can correct this? So the next phase of this is this notion of booking or partition or nested booking limits, excuse me. So nested booking limits would be looking at this plot here and acknowledging the fact that you never want to close this class. The most expensive class, the one that pays more, should always be open. And so we represent this by saying, as long as I have inventory, I'm selling to this class, right? But then you move to the next one. You say, okay, this is the second most profitable class. I certainly want to sell this, but eventually if my inventory is sufficiently low, then I would like to, stop selling to this one. And so we represent this by a bar that is not as long as the class 1, meaning that we're going to restrict to some extent how much we're going to sell to this class. And this value Y1 here represents what is called the protection level of seats that you want to protect to class 1, right? And so this distance that I'm calling here B2 represent the booking limits. So there's a certain amount, right, that you want to allocate to class 2, but eventually you want to protect a certain amount for class 1, which is the most profitable. And the same logic applies for class 3. You want to sell some of these seats to class 3. There's a booking limit, but eventually you want to stop selling to the class because you want to protect some seats for class 2 and 1, right? So this Y2 represents some sort of a protection level for classes 2 and 1 when you're selling to class 3, right? So this is called nested booking limits because they have this, obviously, as you can see in this picture, a nested structure that is somehow trying to take, take care of the fact that you want to stop selling to the most profitable classes, right? So you want to be a little bit more smart, all right? So that's somehow a second phase of, second stage on how you can think about doing yield management. But, there's still a little bit of a issue about how you compute those booking limits and how you respond to this. So I would say the modern way to think about this and how most modern revenue management think about assigning and solving this optimization problem that we're discussing here is through the notion of what people would call bid price, right? And so what is this bid price? So this bid price somehow is a measure of the value for the airline of a seat at a moment in time, right? So it's going back to my original discussion when I was showing you all those applications. And now we're saying what we're trying to do here, we're trying to understand the value of a seat, of a unit of resource. And as I said, that should be some sort of a stochastic process that evolves over time based on market conditions and levels of capacity. But in a practical sense, what that means is that we are trying to construct a curve that looks like this. And one thing that is important is that I need to put some sort of a time. So let me say at time t here, right? So I have a certain time attached to this curve. So this might be a curve 1 month before departure, right? So, and so what happened? You put yourself 1 month before departure and you ask yourself the question, if I have still, say, 40 seats left, how much is the value of one of these seats, the marginal value of a seat, right? And so what you will be trying to do, we're trying to calibrate that estimate. And if this is your bid price curve, you will say that, okay, the value of that marginal seat at when my capacity is 40, let's say in this case, I don't know, $30, right? But then you ask yourself, what would happen for the marginal seat of a seat when I have only 20 seats left? Well, if you have only 20 seats left, like it's still 1 month before departure, this curve will tell you that the marginal value of that marginal seat when you have only 20 left, let's say $60, right? So this curve is representing what's the marginal value of a resource, right? As a function of how much capacity you have, right? And so if you're able to compute this, if you're able to derive this function, now you're in an extremely good position to decide what seats you should sell and which seats you should not, right? So suppose in this example, my 3 classes have prices $100, $75, and $50, right? So if you find yourself here, again, where your capacity is, say, 40, right? And your bid price, I'm going to call it pi here, is, say, I don't know, $40. Well, you can see that at this capacity, when your bid price is $40, you should be willing to sell to all 3 classes because the marginal value of a seat for you is only $40, but every class is willing to pay more for that, right? So this region means that all 3 classes are open. You're selling to everyone here, all right? Now, on the flip side, if you find yourself 1 month before departure and say your capacity is only 15, and now your bid price here is, say, $60, then what's gonna happen here, if you happen to find yourself 1 month before departure with only 15 seats, is that your bid price is 60, which means that you're gonna close this and you want to keep open only class 1 and class 2, right? So the knowledge of this bid price makes your problem of seat allocations trivial, right? If you were to know this bid price curves, you know exactly what to do in terms of what classes should be open and which classes should be closed, right? And so what's going to happen is that, well, we need to compute this. And once we compute them, we're going to be able to somehow answer these questions. Now, the only thing that I want to mention is that this is a dynamic process, right? So this was, let's say, as I said before, this might be, say, 1 month before departure, right? So this is your bid curve 1 month before departure. Now, what would happen if you have only 2 weeks before departure, right? So you start thinking, how the marginal value of my resources will change when you have less time available. Well, if you have less time available to sell your resources, you have less chances to sell, right? There's potentially less demand, which means that your bid prices most likely will be something like this, right? And so this will be, say, 2 weeks before departure. All right. So these bid curves are dynamic curves that change over time. And they change also based on market conditions, right? So as you start going through your selling process, you're going to start learning things, right? Remember on module 4, I think, or 3, I can remember, module 3, you're going to be talking about learning, right? Which means that there's aspects of these demand functions that you don't fully know, and you need to learn about this, right? And so as you start going through the selling process, you're not only trying to allocate resources effectively, but you're also trying to use the data that you're collecting to learn about the market, right? To learn new features, right? New aspects that you might not learn, and use that learning to kind of recalibrate these bid curves, right? So it's a very challenging problem, right? It's a very challenging problem to construct these bid price curves. But if you do a good job building up this bid, the problem of yield management becomes trivial. The problem of deciding how to allocate your resources to what classes, right, becomes trivial, right? And so most of the effort in many of the things that we do is to try to understand how to construct the bid price curves and how to think about this problem, right? Now, implicitly, the way we're going to do this is through the notion of some sort of a value function. So this V here somehow represents a function that tells you what's the value of having X units of capacity. And so Vx minus 1, kind of this marginal value, is precisely your displacement cost, sometimes people will call them, or the bid price associated to that marginal unit of capacity. All right. So let me pause here and see if anybody has questions about this. Everybody with me? All right.
Good evening.
Oh, there's a question, yes?
Is it this bid curve similar to a utility curve in some way? Can we think about it in this way?
Right. So you can think about this function V, right, as some sort of a valuation function that the airline or the service provider is computing to assess how much how much X unit of resource will generate, right, in terms of value. I mean, typically we think about revenues, not necessarily as utilities, right? So we think about this as value, as revenue, how much revenue the companies can make. But one thing that you want to keep in, open mind is that you can replace revenue by other metrics, right? And you can do utility management if you want, right? So maybe this is not necessarily an airline trying to maximize profits, but maybe this is some sort of an NGO that has resources that wants to actually allocate in the market in some sort of effective fashion, right? Like for instance, these days with COVID, many healthcare institutions have limited resources in terms of beds and ventilators and other type of resources that they need to allocate on the marketplace to different healthcare institutions, right? So you can imagine that you can start thinking about doing this type of revenue management allocations where you're trying to allocate these resources as effectively as possible, right? But where you're not really trying to maximize the value in terms of revenue, but rather you're trying to maximize some measure of social welfare, right? And so you will try to replace then the value itself, which is revenue in these examples here. So I put my dollar sign here to represent revenues. You're going to kind of replace that by some measure of social welfare, which could be some sort of a utility, right? And so what we're trying to do here, we're trying to compute that utility function or that social welfare function as a function of the amount of resources that you have X here, right? So I should put a T here, right? Oops, no, not that. You should try to put a, oops, I'm sorry, I'm not. So here, okay. You should put a T here to emphasize the fact that these are functions of time, right? And so you can perfectly change the notion of revenue for something else. I don't know if that answered your question.
Yeah, thank you.
All right, very good. Any other question?
Yes, I have another.
Yes, go ahead, please.
Yes, I was asking about the Vx. As you mentioned, there's a T. So it's the Vx is the price, right? And it depends on the time and market condition. Or it's rather the capacity which depends on that.
Right. So here X represents your capacity. So think of this as X in my plot, right? And think of Vx as the cumulative, revenue or utility, depending on the setting, that the company expect to collect if they have X units of resource available with T time units left, or or at time T, right? So these are functions of time. All right, and so that's why you want to look at the difference, because this difference represents the marginal value of a unit of resource, right? So if you decide to allocate a resource today, you're going to move from the value where you have X units, right, to a situation where you have X minus 1 unit. And so this difference represents the marginal value of a resource for you, right?
Okay. And later we're going to see how this depends also on the demands. Demand curve.
Right. So implicitly, these calculations depends on the demand. Absolutely. Right. So this is where the challenge is how we can calculate this. All right. Very good.
Thank you.
So let me continue. So let's look at the kind of the simplest possible way to think about doing this. Right. And so again, many of these ideas comes from the airline industry. And when you start looking at industries like the airline, you will see that demand has certain patterns, right? And so there's a very intuitive, if you want, pattern, which is that the willingness to pay of consumers tend to increase over time, right? So someone who wants to book an airline seat 6 months before departure, 7 months before departure, is someone that probably is traveling for leisure, is probably have a lot of time to shop around, is probably someone who has, is very price sensitive, right? And so meaning the willingness to pay for that resource is relatively low, right? Now, someone who's trying to buy an airline seat at the last minute when the airline is departing tomorrow is someone who is either in some sort of an emergency, or is going for business, right? But typically that translates to people that are price insensitive or have a much higher willingness to pay, right? And so what the airlines are trying to do is they're trying to use that pattern, kind of what the people would call low before high, to actually create some sort of a segmentation and try to look at this problem in the following way. We're gonna organize the prices and think of S as fare, in this, monotonic fashion, F1 greater than F2, greater than F, say, Fn minus 1. And then they're going to look at the problem on stages. And they're going to say very close to the end, very close to the departure of this, I'm going to be selling in what I call here stage 1. I'm going to be selling to people that are willing to pay a lot, right? And then I move to the next stage. When I'm in stage 2, I'm going to be selling to people that are willing to pay a fare F2, which is lower than F1, right? And so you're going to keep going backwards in time until, say, stage N minus 1. And then again, this might be 6, 7, a year before departure. And at this point, you're going to be selling to a demand that typically is very price sensitive, which has a very low willingness to pay, right? And so what I'm going to think about then is that for each one of these stages, I'm going to try to calibrate the demand, right? How much demand I expect to see from each one of these demand segments, all right? And then I'm going to try to think about this problem as follows. I start with C unit of capacity. I move to stage N minus 1. And I need to decide how many seats I want to allocate to people that are, willing to pay Fn minus 1, right? And I'm going to think of that quantity as Xn plus X minus 1, right? And then, of course, that quantity has to be less than the demand that you face, right? And then if you allocate those units, then your capacity is that is left for the next period is going to be the initial capacity minus how many seats you allocate in this first stage. And then you're going to have to decide again how many seats you're going to allocate to the next stage, right? Let's call that Xn, right? And again, Xn cannot exceed the demand for that segment. And then you're going to keep moving, right? So we're going to solve, or when I think about this as some sort of a sequential control problem, where at every stage we're deciding how many seats we're going to allocate to each of these demand segments. But of course, these quantities are random variables. We don't know exactly how many people will show up. There's a certain random variable, right? And so we're going to try to forecast demand by forecasting the distribution of those random variables. All right. All right. So how can you do this? Well, you can use dynamic programming, right? And so here's where we start, defining that value v. So let's define vjx to be the value function when you have x unit of resources left, and you are at stage j, meaning you're still serving customers from classes j, j-1, all the way to class 1, right? So this is the expected optimal payoff. And so it's optimal because implicit here is that you're going to be doing optimal allocations over time, right? And so this is the best, right, that you can do, right? And so what happened here is that you can write this value function in the following way. At every stage j, when you still have x units of resources available, you're going to ask yourself the question, how many do you want to allocate, right, to this particular class j that you're serving, right? And this is this quantity u here, right? So you're going to try to maximize over u, which is how many seats you allocate, right? And how much are you going to collect when you allocate u units? Well, obviously, you're going to sell each one of those at a fair fj. So fj times u is the current revenue that you're going to collect in this period of time, right? But because you are allocating u units of resources, you're going to have left x minus u units of resources to serve customers from classes j-1 to 1. But if you're doing these calculations effectively, the value of having x minus u units of resources when you start selling to class j-1 is going to be precisely vj-1 of x minus u, right? So this is recursive value function, right? And so what you're trying to do, you're trying to maximize how many seats you want to allocate. And you have to take, of course, expectation because you don't know exactly how many customers will show up, right, when you're serving to class j, all right? Now, this is a discrete time recursive, dynamic program. And the boundary conditions or border conditions that you need to use to solve this recursion is that if you don't have time left, even if you have inventory that is worth nothing. So this is an empty seat. You cannot make any out of an empty seat. And also if you run out of seats because you book them early, you cannot make more, even if you still have more customers that come, right? So these are kind of border conditions that define, that you define somehow together with this recursion, the way you solve for this value function, all right? So you can use dynamic programming to do this. And then you can start, and this is something that typically happens a lot when you do revenue management. And I'm going to give you some reference to read if you're interested in kind of going through some of this discussion.
Can I ask a question?
Yes, of course, please. Let me go back so you can ask your question. Yes.
I mean, I guess like here, one of the implicit assumptions is that people don't cancel their tickets or
sure.
I mean, if
that's
we
right.
have such refunds or cancellations, how is that going to enter?
Very good, very good. So then there's two things that happen. So first, you're going to have to adjust the dynamics, right, of this dynamic program, because potentially maybe at every stage here, I mean, one way I don't want to go too much in the details because this will take a little bit of time, but maybe at every time here you can add something that might look like minus, let's call it G for cancellation times say YJ. So this will be some sort of the fee, cancellation fee that you return. And this is number of cancellations. So you will account for the fact that there's a random number of people that might cancel. And then what you will do here, you will add to this dynamics, you will get X minus U plus say YJ, which is the number of seats that cancel. And then you will need to take expectation over Y as well here, right? Right. And so this will allow you to incorporate another set of dynamics, right, into the dynamic program. that will take those cancellations. Now, of course, if you take a moment to think about this, what's the distribution of this random variable is going to be a little bit tricky, right? Because that's going to depend on how many seats you have booked before in the past, right? How are you going to model that? Are you going to model that any seats that you have booked can cancel with equal probability? Are you going to say that people that pay lower fares are less or more likely to cancel, right? So that will require going deeper into your demand forecast and try to figure out how to use your data to actually calibrate the distributions of these random variables that would become cancellations. The other thing that's going to happen when you think about cancellations is you're going to give the airline the opportunity to start doing overbooking. Right. So if you know that people cancel, then you can sell more than your actual capacity, right? Because there's a chance that people will cancel, right? And this is something that airlines do on a regular basis. They overbook. And maybe you have experienced yourself going to the airport and finding yourself that there's not enough seats for all the people that want to jump into that aircraft, right? So why the airlines are doing overbooking? Because there's cancellations attached to this. So yes, you can add those features into these dynamic programs. But of course, I'm not doing this today because I want to kind of keep it simple in some sense in terms of the basic ideas. But you can see how to start adding those level of a level of complexity, you might say, or more realism in some of these models. Did I answer your question?
Yes, very good. Thank you very much.
All right. So, okay. So what happened? Now you play a little bit around with this value dynamic program. And as I said, this is something that happens a lot in the literature. So if you start reading papers, academic papers on revenue management, you will see that people use this dynamic program formulation to try to understand and gain insights about what is the type of structure of the policy, right? So just to give an example of what I mean by this. So think about this quantity, right? So this quantity by now should look a little bit familiar, right? So we talked already about this displacement cost before, right? So let's call that delta Vj of x, right? Now you can rewrite that dynamic program that I showed you before in this fashion, right? Vjx is equal to Vj minus 1x plus the expectation of Dj of this maximization. Whereas here I did some trick. It's a trick where you start playing with the dynamic program. And I'm not going to give you homework per se, because I don't think this is necessarily the objective of the class but anybody that is curious, I'm going to give you pointers to where I think potential homeworks for you to do. So this would be a very easy homework. Rewrite the dynamic program that I showed you before in this particular form that I'm showing you here. And the reason why this is useful is because if you're trying to maximize and you look at these terms inside this summation, you will see that the only, the value of u here will be the value of u for which each one of these terms here is positive. You're never going to allocate, a resource when this is negative, right? So which means that you're going to keep selling as long as the fare that you collect exceed the bid price or the marginal value of the unit of resource, right? And so we can see that very clearly as showing up in this optimality condition here, right? And so then people say, okay, what can I say about this marginal values? Well, you can say things that are relatively intuitive, like if you fix the time, so if you're selling to a particular segment, J, well, the value of an extra unit is decreasing. So delta Vj of x plus 1 is less than or equal to delta Vj of x. Another way to say here is that your value function V for a given Vj of x as a function of x is concave, right? So there's a concavity here, right, on this value function, right? And the other thing that you can say is that if you have more time, right, to sell, the marginal value of a unit is increasing in time, right? So if you have more classes to sell, then you have more chances to sell it, and therefore the marginal value is increasing, all right? So again, this is a little homework for you. Prove this. This is very intuitive. If you take a moment to think about it, this is extremely intuitive, all right? That's perfectly fine. Now the question for you is, can you prove it? Can you use your dynamic program recursions that I showed you before to actually go and prove this type of statement? And this representation that I'm giving you here is quite useful for the proof of these two statements, all right? Okay, so what does it mean? Well, we already learned that you're going to be selling only if the fare that you collect exceed the marginal value of a unit resource. And then we have that proposition that shows that the value is monotonically increasing over time. And we also show that the value, the marginal value, is somehow increasing in the amount of time that you have, right? So the delta Vj minus 1 is less than the delta Vj. So let's see what happens when you use this in some sort of a practical. If you find yourself looking at this class J and asking yourself the question, how many seeds you should sell to class J and how many of them you want to protect. So here I'm really looking at class J plus 1, excuse me. So you're selling to class J plus 1. Well, you can see that when you look at this bid price curve and this fair, there is this point Yj start where they cross, right? And so when you're in this region, you're accepting class J. When you're in this region, you're rejecting class J, right? And so now, we know how to compute this. And the other thing that you see is that because these two curves are, are decreasing, the protection level of class J star, which is here, is going to be lower than the protection level of class J minus 1 because the fair of J is greater than the fair of class J minus 1. So you can graphically, see when you use these two properties of your bid price that your protection levels are monotonic, right, in the class. All right. So there is this very nice structure now that you can go and implement when you start thinking about how you do your allocation. Okay. Very good. So let's think about this and let's think about maybe how we can go further into calculating those protection levels, right? Can we say a bit more, right? And so, all right, so think about this condition that we just kind of derive and these protection levels, which are, as you remember, nested because of the nature of the fair classes. So the basic, one-on-one, yield management formula has a name. It's called Little's Wool rule. And this is kind of the formula that will help you compute these protection levels when you have only two classes, right? So you have two classes. Again, there's a fixed capacity C. Fair 1 is greater than fair 2. You have random demands for each classes. And, as we said before, demand 2 are right before class 1, right? So what you would like to do, you would like to figure out how many seats you want to protect for class 1. So you're selling to class 2, remember? And then you need to decide eventually you want to stop selling to that class and protect some seats for the high fair class F1, right? So again, you can go and do the dynamic program that I was showing you before, which can be used in general. But there's a very simple, intuitive way to think about this. And I think it's useful to kind of build that intuition, right? So suppose you're selling to class 2. So class 2 is open, right? And eventually you're asking yourself the question, should I stop selling to this class and should I protect for the next class, right? So if you accept a class 2 request, you collect F2. That's the fair, right? And so you can get that, on your pocket. Or you could reject. And if you reject, what happened? Well, now you start selling to class 1. Now, how much are you going to make if you protect to class that seat for the high fair class? Well, you would say, okay, I'm going to make F1, that's the fair, but only and only if you sell that seat, right? And so then what's the likelihood that if you protect, you're going to sell that seat? That is equal to the probability that the demand that you're going to see for the high fair class is greater than the level of inventory that you have at the moment that you're making this decision. So Y1 here is that level of inventory that you have when you're making this decision, right? And so what happened is that if this fair F2 is greater than this, right? So if this is greater than this, you're going to accept the fair 2, you're going to keep selling, right? And if this is greater than this, you're going to reject, right? And so at optimality, and there's an issue here of whether these distributions are discrete or continuous, but if we assume that these distributions of demand are continuous, then at optimality, you expect F2 to be equals to F1 times the probability that D1 is greater than Y1, right? Which is what I have actually here. So that's your optimality condition, right? And from this optimality condition and with, the demand distribution that you have for class 1, you can infer what is the optimal protection level for class 1, right? And so this has a name. This is a Littlewood rule, which kind of tells you how many seats you should protect for class 1 when you're selling to a 2-demand class. All right, makes sense? And then from this, you can kind of say what would be the corresponding booking limit and what's the corresponding bid price here. So the corresponding bid price of resources at that moment in time will be given by this function that I have here. Everybody with me? Yep. All right. So now take an example. Let me move away from, maybe airlines. Like, so you've got a hotel. You have this hotel is selling two fare classes. So you have the discount one at 105, the full at 159 here. And so of course you are never going to reject these guys. These are the ones that are paying the high price, but you might want to start rejecting eventually these people, right? Now you take this kind of setting where we have low before high. So what we assume these guys are very price sensitive, but they book well in advance, right? So that's when we start selling to them, 3-4 months before the date of arrival, which would be say March 29 here. And then you have these business travelers, right, which are more price insensitive. The company pay for their ticket, for their trips, but they tend to book at the last minute and the demand is more uncertain, right? And so the question for the hotel would be, okay, I want to sell to these guys. Of course, I have 210 rooms. I want to sell some of them, but how many? And when should I stop selling to these people? And when should I start protecting capacity for these people here, right? So, well, you can use your, you can use your Littlewood rule here. So this is kind of the information that I gave you before. And let's say here you have a history of a transaction. So your demand here comes in the form of a table of data that you might have collected, right? So here you look at the 123 days that looks like the one that you're going to be booking, and let's say 12 of them the demand was less than 70, right? And 3 of them the demand was 71, and so you have these frequencies, and you compute from this some sort of an empirical demand distribution, which is the probability that the demand is less than a certain amount, right? And so then you go, whoops, and then you go and you use your Littlewood rule, and your Littlewood rule says you want the fare, the discount fare, to be equal to the full fare times the probability that the demand, I'm going to call at full fare, let me call that the F for full fare, right, is greater than the amount of capacity that you're going to protect. Let me call this Y1 or YF, how many you're willing to, right? And so from here, you want the probability of your demand at the full fare greater than your protection to be equal to 105 over 159. And so from this, right, if you get the distribution, the probability that the demand full is less than or equal to YF has to be equal to 1 minus 105 over 159. And this is equal to 0.3396. And so then you do the inversion, which in this case, you look for the value of YF that satisfies this equation. And so that's going to happen somewhere here, right? Somewhere in that region. And so from this, you get that your YF is equal to 79, in this case, rooms, right? And so then what the hotel should do in this example, they should sell, to the discount as long as the remaining inventory is more than 79 rooms. But as soon as your inventory hit this threshold of 79 rooms, you close the discount fare and you reserve those to the full fare, right? That's how you do, yield management. That's how you do revenue management. Make sense? Very simple, but again, very, very efficient. Now, what would happen if instead of having 2 demand classes, you have n demand classes, right? So there is this paper by Brumel and McGill that I mentioned, I believe, in the syllabus that, mini syllabus, I should say, that I distributed, that actually takes care of this. And what they do in this paper, they just simply generalize Littlewood rule to n classes, right? And the way it works is by constructing these field rate events, right? So this is the event that we just discussed. The demand for the high fare greater than the protection level for the high fare class. The next field rate event will be the demand of the high fare is greater than the capacity of the of the protection level for the high fare, and the demand, the sum of the demand of the first and second highest demand classes greater than the protection level for Y2. And then you just go through this sequence of field rate events, and then you compute these protection levels, Y1, Y2, Yi, by solving somehow the equivalent of Littl's rule, right? Where you have this, the probability of this field rate have to be equal to the fair of the I+1 divided by F of 1, all right? So very quickly, how this would work, let me just kind of show you this. So let's think about this together. So we can do essentially, so take, so let's say class 3, right? So we're selling to class 3. So let's do the first two. So if you're selling to class 3, if you accept, you collect F3. Now, if you reject, right, you need to ask yourself the question, what's the revenue that you collect if you reject exceed to class 3 and you start trying to book that into class 2 and class? Well, two things can happen. Well, you can sell that at the price F2, right, which is the next class, but only if the demand for this class is sufficiently large. Larger than what? Larger than the inventory that you have at this moment, Y2, minus the protection level that you have for class 1. If that happens, you're going to be selling that seed to class 2, right? But you can also sell that seed to class 1, right? How? Well, for that to happen, you need to have a demand for class 2 that is not too high, meaning that you, right, it's less than the difference between Y2, which is your current inventory, and the protection level for class 1. But then the demand for class 1 has to be very large, larger than what? Larger than Y2 minus D2, which is the demand that you're going to see for class 2. All right. And then what you do with this, the first thing that you do is to use your Little's law here, because you know that F2 is the same as F1 times the probability that D1 is greater than 1. That's, we just learned that optimality condition for the last class, right? Times the probability that D2 is greater than Y2 minus Y1 plus F1 times the probability of this joint event, D2 less than Y2 minus Y1. And this is the same as D1 plus D2 greater than Y2. And then you can see that these two events are independent. We're assuming that these two events are independent. And you can see that these events on, right? So this event and this event are disjoint because of this. And so you can just combine this and write this as F1 times the probability that D1 is greater than Y1 and D1 plus D2 is greater than Y2, right? So of course, these two events are complement to each other, right? And so that's precisely the field rate for, right, for the second class. And then at optimality, what you want is that this is equal to F3, right? And so that's your kind of Little's rule, but for not for 2 classes, but for 3 classes. And so this kind of idea extends, and so you have this this result that I was showing you before, right? Here that, and you can read that paper that generalizes this, right? Now, the challenge of this is how you compute the probability of those events, right? So this can be very tedious. And so there's another paper by Robinson that actually shows you how to do this using Monte Carlo simulation. And so that's how you can try to do this. Now, of course, this is theoretically very sound, but again, this is where practically might not be very useful for an airline. If an airline needs to start doing all this Monte Carlo simulation in order to kind of compute these protection limits, it might take too much time and it's not the work, right? And so there's a bunch of heuristics that have been proposed. The simplest one, or one of the most popular one as well, is one by Peter Berlobaba. Who's someone who actually works at MIT. He has a center where he does a lot of consulting for airlines and a lot of simulation actually for them. And so he came up with this policy, which says, you know, how we should do this? Well, let's try to use Little's rule as much as we can, right? And so he said, when we're selling to class J plus 1 and we're trying to decide how many seats we should protect for classes J and J minus 1, why don't we do the following? Why don't we take all these classes, J, J minus 1, and we combine them into a single aggregate class, which is some others demand, right? So these are stochastic random variables. So we just sum all those random variables to get some sort of a cumulative random variable that represents the sum of all these classes from j to j minus 1. And then we replace the fare of all these classes by some sort of a weighted average fare class, right? So we take the fares of each one, but we take weighted average where the weight is based on the demand, right? And so when you do this, right, you're selling, to class j plus 1 here, and then you have this kind of fictitious class, right, which has a demand sj and has a fare fj, right? And now you pretend that you are in a two-class problem, right? And you're trying to say how many seats to set here and how many to protect to this class where you have only these two together, right? So it's some sort of a trick or a way to aggregate things. And then this can be implemented. So this will be an example. I'm going to go quick here, but this will be how you can use this EMSRP. You have, these four classes, right? The prices goes down. This is the estimate demand. Think of them maybe as normal random variable with a mean and standard deviation. And then what you will do when you're trying to sell to class 4, you got to aggregate all these three classes. And so when you aggregate these three classes, what's the mean? You sum the means, which is 140. What's the standard deviation? Well, the standard deviation of you sum this, the variance of this, and you take the square root, you get this. And what's the fare? You take the weighted average of this fare by this means. So when you do the weighted average of this fare by this means, you get 283. And now you can use your little rule where you have this fare class and this kind of fictitious class that you're selling, and this gives you 147, which means that you're going to sell to class 4 as long as you have more than 147 seats left. When you hit 147, you stop. And then you can do the same thing when you're selling to class 3, because you're going to aggregate these two, and these aggregates will give you this, right? Now, the mean of the aggregate will have a mean of 70 and a standard deviation of 11. The average fare of these two with this weight will be 370, and then you compute the protection level, and it's 68, which means that you're going to be selling to class 3 as long as you have more than 68 seats. After that, you stop, and so on, right? So now you have a very simple, if you want, rule that is very practical, right? It just uses this little rule sequentially, and as I said, it's very popular in the industry. And so here, I think you want to take a moment to kind of go back to what I said before, which is, revenue management is theory, but it's also practice, right? So we have a theory that tells us how to compute these protection levels, optimality by solving those field rates calculations that I showed you before, but that's not necessarily the most practical way of doing. And so here you have a heuristic, which is very basic, based on this two-class little rule, but it's very popular out there because it's actually does the job quickly. And so sometimes good revenue management is looking at the theory, but then also finding ways in which you can simplify that theory or approximate that theory in a way that you get rules that are practical and implementable. All right. Okay, so let me continue. Now, let's look at some sort of the general problems, right? So what happens if we don't have this low before high? What happens if we just people coming, right? And so if you think about this, and this is just in the case of two classes, but if you think in terms of two classes, the kind of problem that you will be solving will be, again, stochastic control problems, which will look like this. So again, with two classes, you will be solving a problem that looks like this. You're trying to find for a sales strategy. So think of S as dynamic stochastic controls that represent how many seats you want to sell over time. And in particular, at time capital T represent how many seats you have sold for class 1 and class 2. So what we're trying to do, we're trying to maximize the expected value of the revenues that we can collect from these two classes, right? Subject to what? Subject to the sum of S1T plus S2T has to be less than your capacity. Now, these are stochastic constraints. So actually, I should put this almost surely, because this constraint have to happen almost surely, right? You also want that the sales process of class 1 cannot be higher than the demand process of class 2. You cannot sell more than the demand that you have set. And again, these are almost surely constraints, right? And then you have that S2 cannot exceed, again, the demand for S2. And then again, this has to be almost surely constraints, right? Now, of course, Your stochastic control problem has to be practical, which means that this control that you are building up have to be non-anticipating, right? Non-decreasing, of course. Well, that could change if you have, someone raised the question of returns, right? If you have returns, possible a return can be a negative sales, right? So in that case, with return, the non-decreasing behavior is not necessarily. You can potentially have decreasing trajectories if you have returns, but of course you don't want this to be anticipated, right? You cannot see the future, and therefore, of course, these constraints have to be adapted to the filtrations that are generated by the cell process of these two-dimensional classes, right? So this is somehow the type of objects that we will be like to solve when we start kind of looking at potentially the most general version of this problem that I have been discussing with you today. Make sense? So, all right, so how can you do this? Well, you can formulate this if we make it, if you add some assumptions, we can start turning this into some sort of a Markov control type of problems, right? And so the fundamental assumption that people have made in this literature is to think that demands follow some Poisson process, right? Some, you know, you can generalize this to, you know, point processes that need some intensity, but, you know, the Poisson process is by far the most simple, intuitive, and in many ways practical, because it's not necessarily a bad assumption to assume that demands for some of your products might follow a Poisson process. And so what would happen if you think about this in terms of a Poisson process? So let's call DIT your point process demand for your Poisson process for class I, and let's say that has an intensity lambda I of t. So the problem that you're trying to solve will look like this. You're trying to maximize the expected value of the sum of your revenues. And again, we're summing over all the product classes that we have. There are n of them. Each one generates a profit that is somehow the stochastic integral of the fare that you collect times u. So here u represents this binary control that tells you whether the class is open or closed, right? So if the class is closed, so if ui is 0, then you're not selling to that class, you collect nothing. But if ui is 1, that means that that class is open. And so every time that you have a jump in the process, you're collecting a revenue of fi, right? So this stochastic integral represents the revenue that you're collecting from selling to class I. And then you have your capacity constraints that you cannot sell more than your capacity, right? And so you want this, the sum of all the units that you're selling across all the n classes cannot exceed the capacity C that you have, right? And again, this should be almost surely. And then this control again have to be adapted to the demand process that we have, right? So what would happen is that you can formulate this problem using dynamic programming. And so in this case, you have some sort of a version of that dynamic program that I show you in discrete time, which is the AGB, the Hamilton-Jacobi equation would look like this, right? So the partial derivative of your value function with respect to time, right? Or the negative of that partial derivative with respect to time is equal to this expression here that represents somehow the instantaneous revenue that you make, which is again, you're summing over I equals 1 to n of lambda I, which is some sort of the intensity at which the jumps occur. And every time that the jumps occur, you will collect how much? You will collect, well, the revenue, Fi, but you incur some sort of a loss. And this loss, you can write it down. Maybe you can write this as Fi Ui minus delta, right, of Vt, should say delta V at time t of x, x, right? So x, I should put delta xu to emphasize the fact that if u is 0, then there's no delta because u will be 0. But if there's a 1, then you will have an increment, right? So you have essentially the same type of term that's popping up here that is telling you that you only want to sell when the fare that you collect exceeds the bid price of that particular resource at that particular moment, right? Now, because of time, I'm not going to show you how to solve this, but the way you will solve this, and some of you might, let me just quickly mention this. The way you will solve an equation like this is recursively backward in x, right? Why backward in x? Because if x is equal to 1, then Vtx minus 1 will be Vt of 0, which is equal to 0, right? And so you have an equation that looks like minus dv of 1 dt is equal to the max over u of the sum from I equals 1 to n of lambda it times f I ui minus v t of x, right? So that's how sorry, too quick here. I went too quick. So minus this delta vt of xu that I was mentioning before. But of course, you know, you're only going to sell if this is if this difference is positive. So this is the same as the sum from I equals 1 to n of lambda it times f I minus this delta bt xu positive part, because only if that is positive you're going to sell, right? So if you think about this, you are left with some sort of a non-linear ODE, right? Because this the border condition here allows you to get rid of this term here when u is equal to 1. So you can solve this, and the way you will solve this is by saying, well, if you're really close to the end of the selling horizon, you expect that all the classes should be open, right? If you have very little time left and still have capacity, you want all the classes to be open, right? And so essentially you will look at this time horizon from 0 to t, right, capital T, and you will say there's some sort of a tau n here, where here all is open. All classes are open. And then you can rewrite this ODE, which is nonlinear, as a linear ODE in this region, and you can just solve for that. And then you'll say, well, if you're not too close to the end of the horizon, maybe here you want to have everything open except all open except class N, which is the less profitable one. And then you will keep going like this. And so in each one of these time intervals, you're going to be solving a particular ODE. And what you need to do is you need to kind of find this points at which these different ODEs will meet. So you need to impose value matching on the different pieces that you're solving. And so you will solve this backward on time, and you will do this for x equals 1, and then you will need to do for x equal 2. And so it's very, very tedious. Of course, there's no big theory in terms of how you solve these ODEs. It's only that it's very tedious, right? So again, what people have done, they have said, well, why don't we use approximate dynamic program, right? And so this is the kind of thing that you will see happening in many, many papers in revenue management, is that we have these optimality conditions, we have these AJB solutions for these problems, we can potentially solve them numerically, right? But it's tedious and in some sense not practical. So why don't we use approximate dynamic programming? And so what we learned from that AJB is that we are trying to find some sort of an estimation of the value function that will allow us to do this type of calculations effectively. As long as I know my bid price that I was mentioning before, I should know which classes are open and which classes are closed, right? And so different people will do different things. So Baba proposes some sort of this way to think about, you know, just aggregate things and use these simple calculations, right? Some people have said, why don't we just replace all the stochastic random variable by their means, right? So I'm replacing the means of the demands here. And so this is called certainty equivalent, where everything is, all the random variables are replaced by means, and now you solve some sort of a deterministic problem, right? Other people say, why don't we use this anticipative version, which is, let's pretend that I can see the future. And so if I can see the future, I can calculate this allocation as if I knew the demand, and then I take expectations of that. So all this will give you approximations for the value function. And then what you do, you use that approximation to calculate this quantity. And then you accept or reject based on whether this is greater than this, right? So these are very simple. And so you can calculate it. And so this is an example of how this will look in a particular instance where I implement these different policies. And as you can see here, for each one of them, I can evaluate their performance. And for instance, the Velobaba out of the certainty equivalent, and the anticipative is the one that performs actually the best in terms of performance, right? So this line of research would essentially do this. We'll take a problem, come up with a nice, intuitive, practical, and with hopefully with some performance guarantee approximation, and then use that as a mechanism to construct an approximation value function and use it and implement it. And then do the work to actually test the quality of that approximation and try to prove performance values. I know I have a minute left, but I just want to mention one of them. So this is fluid approximation. So the fluid approximation will go back to the problem that I was showing you before, right? Where we have this stochastic integrals with respect to Poisson process. We look at those integrals and we'll say, okay, let me decompose this demand process into their martingale components and their compensators, right? So here mi will be my martingales. And then when I replace this here, of course, the integral that's with respect to the martingale here will cancel. So you have a problem that looks like this, right? So these are my constraints. And then what I will do, I will just get rid of this stochastic integral with respect to the martingale and on the constraint. And so what you have now is that when you cancel this in stochastic integral, you have a problem that is deterministic, right? There's no more uncertainty. And so people call the certain equivalent or the fluid version of this. Now, the first thing that you learn and you can prove, and again, this might be a nice exercise for you, is to prove that actually the true value function for the stochastic problem is bounded by the fluid approximation of this problem, right? So this represents an upper bound. The other thing that happened is that when you solve that simple fluid approximation, you can, reorganize your decision variables and just solve as a static knapsack problem. So this is just an LP problem that you solve, which we know how to do very efficiently, right? Actually, a greedy will solve for this. And then when you have the solution for this problem, right, you can say, okay, let me use that greedy solution and construct a stochastic policy, which is essentially says, all right, let me accept as long as the number of units that I have accepted in this particular class doesn't exceed the solution that my fluid approximation, my linear programming is reporting, right? And then you can ask yourself, well, is this a good policy? Well, and it depends, but there's an asymptotic results that actually makes this policy appealing. Because if you take that policy, that fluid solution, and use it in environments where your capacity, CK, grows large and your demand grows large, so instances where you have more and more seats, but you have more and more demand, so this is an asymptotic regime that is happening here, then you can prove that essentially this policy, which is just a heuristic, converges in distribution and in expectation to that upper bound that I showed you before. In other words, is optimal. So this fluid solution, right, that solved that simple knapsack problem is asymptotically optimal in regimes where you have high demand and high capacity, right? And so that means that the policy is not completely crazy. It's actually a policy that can perform extremely well in environments that meet this asymptotic regime, all right? So I'm going to talk more about asymptotic analysis next class on Wednesday. So maybe some of these ideas that I flesh out rapidly today will become a bit more clear on Wednesday. But I just want to finish with this so that you get a bit of a sense of how revenue management goes from the theory to approximations, and then how you can prove performance for this. All right, so I want to finish with this. This is a set of references that talks to many of the things that I discussed today. My understanding is that both the recording and the slides will be posted on the website of the class. So you should be able to kind of take a look at this and also maybe take a time to look at these references if you have the time. All right, let me stop here and I'm happy to take any questions if there is any. All right, no questions?
I guess everything is clear now.
All right, okay. All right, well, thanks everyone. Hopefully this was useful to kind of give you some sort of an introduction to revenue management and the type of things and challenges that we face. And next Wednesday, we're gonna talk about network revenue management when you have not just one resource, but a network of them. And then finally, we'll talk about dynamic pricing next week.
Thanks a lot, René. Yeah, so basically we'll see you all hopefully on Wednesday, and then it's basically the references are there for you, and we'll make sure to have all the slides and the recording as soon as possible on the website.
All right. Take care. Have a good night,
Thank you,
everyone.
Thank you, everyone. Thanks.
See you. See you soon.
Have a good one. See you Wednesday.
See you then.
Bye.